The human retina is endowed with the specific sensitivity to detect electromagnetic waves between the 400 and 750 nanometer wavelengths. We call this narrowband light, the primary data stream we use to interpret the physical world. Light propagates through a vacuum at an enormous finite speed, accepted today as exactly 299,792,458 meters per second. But our intuition that light travels straight contradicts the reality that it is an electromagnetic wave. Waves oscillate. They bend around solid obstacles. We reconcile this through scale. Because the wavelength of visible light is vanishingly small compared to the everyday objects it interacts with, the wave behavior becomes negligible in most macro environments. We can accurately model the propagation as a straight vector. The mathematical path of this vector is a ray. A collection of these parallel paths forms a beam. This ray picture of light provides the geometric simplification required to trace reflection and refraction with total mathematical precision. To construct formulas that reliably predict the behavior of light across any spherical mirror or lens, we require a standardized system for measuring distances. This diagram shows the Cartesian sign convention. The geometric center of the spherical surface, the pole, acts as the 0 point. Distances measured in the incident light's direction are positive. Conversely, distances against the light are negative. Heights upward are positive, and downward are negative. Adhering to this specific coordinate grammar ensures that our final optical equations can correctly locate images, whether they are real or virtual. Here we see a schematic of a single spherical interface separating two transparent media with different refractive indices, air at N1 and glass at N2. We place a theoretical point object O on the principal axis. A light ray travels from the object and strikes the curved surface at an exact coordinate, point N. The normal perpendicular to the curve passes through the center of curvature, point C, forming the angle of incidence, I, with the incident ray. Entering the denser glass, the ray bends toward the normal, creating the angle of refraction, R. To solve the geometry, we limit our focus to paraxial rays. These are rays that make extremely small angles with the principal axis, striking the surface very close to the pole. Under these tight conditions, the slight curve of the glass near the pole is mathematically indistinguishable from a straight, flat perpendicular. Locking our normal line to the center of curvature gives us the geometric framework needed to apply Snell's law of refraction to a curved boundary. We begin with Snell's law. The refractive index of the first medium times the sine of the angle of incidence equals the index of the second medium times the sine of the angle of refraction. Because paraxial rays operate at such small angles, the sine of the angle is nearly equal to the angle itself. We drop the sine functions entirely, simplifying the law to n1 times I equals n2 times r. Next, we evaluate the geometry. Looking at triangle ONC, the exterior angle of incidence I equals the sum of interior angles at O and C. Using triangle NCI, the refraction angle R equals the angle at C minus the angle at image point I. We substitute these definitions for I and R straight back into our simplified Snell's law equation. Because small angles and radians roughly equal their tangents, we replace the angles with the ratio of point N's physical height over their respective distances along the principal axis. Since the vertical height, Mn, now appears in every single term, we can factor it out completely. The vertical height of the incident ray cancels itself out. Now we apply the Cartesian sign convention. Object distance is negative u. Image distance is positive v. Radius of curvature is positive r. Distributing the refractive indices and isolating the variables places the object and image terms on the left and groups the geometric radius on the right. This yields the final equation for spherical refraction. N2 over v minus N1 over u equals N2 minus N1 over r. This layout shows the variables for a practical test of the equation. We have a point source of light in air, located 100 centimeters away from a convex glass surface. The glass has a refractive index of 1.5 and a radius of curvature of 20 centimeters. We insert these specific values into our derived equation. N1 is 1, N2 is 1.5, U is negative 100, and R is positive 20. Simplifying the fractions gives us 1.5 over V plus 0.01 equals 0.025. Isolating the image distance, v, yields a result of positive 100 centimeters. This indicates the light rays will converge to form a real image exactly 100 centimeters deep inside the glass medium. The algebraic derivation perfectly maps to the physical behavior of the light. A standard thin lens is constructed by taking two of these spherical surfaces and placing them back to back. The image formed by the first refracting boundary simply serves as the virtual object for the second. Applying our single surface equation successively to both sides generates the universal lens maker's formula. The geometry of one curved boundary provides the mathematical mechanism required to understand how light focuses. It's the exact physical principle operating inside cameras, inside reflecting telescopes, and the human eye itself.